I will make this necessary preparation. So, today we will consider open covers. What about open covers? First, I suppose that you know what this word means. A family of open sets which cover the topological space. That is, the union is the space and nothing else. This is an open cover. For a manifold, there exists a very special open cover which is provided by an atlas. So if X is a manifold, and this is an atlas, then the sets, the images of these maps they open, and then so alpha is the number of some set A, set of indices, and this is an open cover. By definition, a manifold has a countable, at most countable atlas, so there is at most countable open cover. For purely technical reasons, we may consider sort of better countable open covers. Namely, take some countable atlas like this. Well, this is U alpha. Within U alpha, we'll consider all open. So this is radius R, X is the center, all open balls with rational radius and rational centers. So the centers have rational coordinates. It is very clear, also certainly we can waste several lines of proving, but I will not do it. It's very clear that balls like this cover any open set in Euclidean space. And if you restrict the chart U alpha phi alpha to this set, then we will get a new chart. So alpha is the number of this set. And this is another countable atlas. There are countably many balls with these properties in every open set in space. So this is actually, it is very clear for the, I will denote this covering by script W. I will use it several times, only today. I am not sure that we will ever need it again. I want to say that actually, if we have an arbitrary open cover of X, then we can take a part of this set. So let me say W sub U consists of those W. This is, excuse me, this is not a covering. Covering is, let me say, phi alpha of this. Yes, so this is an atlas. And the covering is the set of sets. So we consider those elements here in W, so that there exists some U in U, so that W is in U. So we consider an absolutely arbitrary not necessarily countable covering of X. And then we take those elements of this covering which are contained in the elements of this. And what I can say, certainly this is countable because this is what is important. It is also a covering. It is again obvious. It's clear that within every U, sets like this, sets like this cover every U, and hence they cover the whole manifold. Again, probably in my notes there are several lines, maybe 2 lines, 3 lines, but I will not repeat it. So this is also covering, and this is a countable covering. So what I can say that for every covering, I can find a countable of X. I can find a countable covering, which, as people said, inscribed in U. Let me make legal this term. So we have 2 coverings, V and U. Then V is inscribed in U if for every V in V there exists a U in U, say that V is contained in U. So what we have there, we see that every open cover, for every open cover there exists another open cover which is inscribed, countable open cover, which is inscribed in it. There exists, in other terms, strongly inscribed. And strongly means all the same. Only V bar is contained in U. So for every element, every set covering V, there exists a set from the covering U which contains the closure of it, strongly inscribed. Here certainly we can make this inscription strong. Simply take those element W whose closure is contained in elements of U, and again this will be covering. This will be a cover. If we speak of terminology, let me introduce 2 more words which we'll use today regarding open covers. We say that in open cover, so U is an open cover. U is compact if U bar is compact for every U in U. So open sets are not compact, but their closure may be compact. So compactness in open cover is a requirement that every closure of every element of U is compact. Certainly, we can easily make this double covering compact. Simply, we should, so here, not here. So simply we need to slightly modify the condition for dxr, that not dxr belongs, is contained in U, but rather the closure of it, closed ball. Not a big deal. And so now we have this proposition that every covering of X, for every covering of X, there exists an actually compact countable open cover, which is inscribed, strongly inscribed in the given cover, and from this, by the way, it follows that every open cover of X contains a subcover which is countable. What is a subcover? Simply we take the same covering and take just some sets of it, not all of them maybe. This is a subcover. Now take a countable covering which is inscribed, strongly or not, in a given covering, and for every element of this countable covering, take the element of the given covering which contains it. So you understand the picture. We have U covering. This is U. Then there exists also another covering which is countable, compact, and is inscribed in U. Then for every element of this countable covering, we take some element, maybe it's not unique, of the initial covering which contains it. Again, we have a countable family of open sets. It is a subset of the covering, and it certainly also is a covering because it every point is contained in some element of this covering and hence in some element of the big covering. So what about this? So far nothing. It is all obvious. Now I need to discuss three less obvious, how to say, equally boring but less obvious properties of open covers. And one of them has a common word in topology. And this word is paracompactness. By the way, when I introduced the terminology, I now understand that I wanted to give one more term. Have you ever heard of it? A covering may be locally finite. What could this mean? Locally finite. Actually, any, how to say, family of subsets may be locally finite. A covering is locally finite, so let me write it here. If for every point P in X, there is a neighborhood V, such that V intersection with U alpha is can be non-empty for only finitely many alpha. So this covering, it is infinite. Yes, it is infinite. But locally, it is finite. That is, if you take a point, then in the proximity of this point, you can see only finitely many elements of this covering. The covering itself may be very much infinite. Do you understand? Yes. Now, paracompactness. This is a word which, allowed in point set topology, means slightly not the same that I need. Actually, the usual mean. Do you know this word? Have you ever heard it?
I've heard it.
We heard, but you don't remember what it is.
No.
I will say this to you. You will remember it. Excuse me. It's not very interesting. So, a topological space is paracompact if every open, if for every open cover there exists an inscribed or strongly inscribed modifications of this definition, a locally finite cover. So we have an open cover which actually is absolutely arbitrary, and we want to find a strongly inscribed subcover which is locally finite. It is important. Locally finite objects are generally important in mathematics. I can give you a hint why. Imagine that you have a family of functions on your topological space, which have, how they say, supports in elements of in some covering. A support of a function is the closure of a set where it is not equal to 0. So a point does not belong to the support of the function if the function is 0 at this point and in some neighborhood also. So functions have supports. Suppose that you require that supports form, again, family of sets inscribed in a covering. So we have a covering and family of functions, say indexed with the same indices that the covering. We have U alpha, we have F alpha. And we require that F alpha, that the support of F alpha is contained in U alpha. Do you understand this? Then if the covering is locally finite, but only in this case, you are able to take the sum of all these functions, such an infinite sum, maybe very much infinite. Because at every point, the sum is finite. And it will be have more or less the same properties. Smooth if the functions are smooth, continuous if they're just continuous. So it is something like uniformly converging series. Do you know what I say? We will apply these constructions several times. But now I just want to say locally finite may be very useful, because it is very inconvenient if a point belongs to infinitely many, even to the closures of infinitely many sets. Then you are not able to apply such constructions as infinite sums. Yes, so power compactness. And now theorem. The short statement is manifolds are power compact. I give a more precise statement. If we have a manifold, so a theorem, proposition, whatever. Let U be covering of a manifold X. Then there exists a compact, locally finite covering of X, which is strongly inscribed in U. So for every covering, we can find another covering which is strongly inscribed in this covering and which has, in some sense, all good properties. Compact and locally finite. I don't need anything else of it. Strongly inscribed. Do you understand the statement? The proof is less interesting than the statement, still it involves a picture. First of all, before I say anything, certainly if I have this covering U, I don't need to prove it for this covering U. I can replace it by any covering strongly inscribed in U. If V is strongly inscribed in U, and I prove this for V, then it is automatically, because what is actually even inscribed. If V is inscribed in U, and I find a locally finite compact covering strongly inscribed in V, then it will be also strongly inscribed in U. So I can apply my previous constructions to make U slightly better before proving this theorem. Namely, I suppose we can assume that U is a subcover of W, which was defined before. That is, all elements of U have this form. We have, so what is U? Consists of D. So every U alpha is some is an image of an open ball. An open ball in space with rational. It is not important actually that everything is rational. Just a ball like this. Still countable. So maybe it's not important, but it is reasonable to assume that this new covering is W is countable. So we take some atlas on this notation. U alpha actually means not the same as before. We take some atlas of X. Then for every chart we take balls with rational centers and rational radii which are contained in this chart and have this. Maybe it is better to actually, excuse me for these change notations. Now this is W alpha. So W alpha is my covering. No, since it is countable, I prefer to have W1, W2, and so on. So I just label them by the integers. Fine, the integers is not important. And this is my new covering. So my new covering has this property that every set is an image with respect to some continuous maps of a ball in the Euclidean space. So I replace my covering U by a covering with these geometric properties. Is it clear? Now, so this is not locally finite, but now I will make it locally finite. In the following way. First of all, for every W, I can consider such a thing. Fix any number T between 0 and 1. And write TW, which means, so TW is phi alpha of dx tr. So what I'm doing, I take the same ball and shrink it. Multiply its radius by t. T is a number between 0 and 1, not 0, maybe 1. And then I denote this as t. So you understand that for every Wi is Wi. I have this TWI, which looks like this. Now I define a new covering. Look. New cover. V1 we will W1. V2. It is W2 minus 1/2 W1. What does this minus mean? 1/2 W1 is not contained in W. So I sweep away everything in W2 which belongs to 1/2 W1. Then V3 is W3 minus 1/2 of W2 before, let me draw it. It is W4, well, it may be also a disk. I drew it like a disk, actually, it is in a manifold. It is W4. This is W3, this is W2, and this is W1. And then I delete from W1 this which actually doesn't touch W1, and this. It is 7/8 W1. And this will be V4. So V4 my statement. This is a compact, locally finite, covering inscribed in W, in my covering W. So if W is strongly inscribed in U, then my theorem has been proved. Is the statement clear? This is my construction. I will not do anything else. So where to begin? Why is this covering? Nothing can be more obvious. W was a covering, right? So every point of X belongs to some W, to some sets W. So a covering. V. The natural foundation is V. V is a covering. Why? This is because if P is an X, then P is contained in some Wi. We can choose this I in such a way that P is not contained so I is the smallest number for which P is in Wi. Should exist. And then P is in Vi. Certainly when we form Vi, we delete something, but the something doesn't contain P, because P is not contained in any of sets which we delete. Done. Number 2, compactness. Double Vi is a closed subset. Closure of Vi is closed. Very deep, right? Closed subset of a compact set. By this reason, it is compact. Locally finite. Well, this is sort of for something for which this construction was made. Why is locally finite? Take a point P in X. Then P is contained in some Wi. This is Wi, this is P. Then it is also contained with a neighborhood, actually. Also contained in 1 minus 2 minus n. In 1 minus 2 to the power minus n of this W. W is an open disk. So actually P is closer to the center than the radius of this disk. We can always do this. So P, even with some neighborhood, is contained in this. But when we form Wm, if M is at least n, then it is Vm. Then it is Wm minus something, and this something is contained at least this. So I believe we need to write n plus I here. You remember, we delete from when we construct W with big, when we construct V with a big number, we should delete from Wm almost all. W1, W2, right? And certainly if the number is big enough, we will delete P with its neighborhood. This is the proof. All done. Questions? Maybe this is the most difficult theorem in all this theory. Questions? There, question? No? Yeah, we were good with questions some time ago. Maybe now? It will help me. Not yet, I see. You don't want to help me. Well, not obliged. Next result looks funny. Shrinking. We have a covering, open cover of a manifold, which we can assume good. Say compact and locally finite. This is for the purposes of proofs. The result actually is true for any covering, any open cover. We have a good open cover. Good means now for us that it is compact and locally finite. I want to shrink it. What does it mean, shrink? Well, so this is U alpha. Now, to shrink means that for every U alpha, you find a V alpha inside it. Such that, first, the closure of V alpha is contained U alpha, and second is that still this V alpha is also covering. So the sum union of all V alpha is X. Sometimes it will be important for us. We have a covering, and just to perform some construction, we want to shrink it a bit. Let us take smaller neighborhoods. How to do that? Again, there is a construction which I will show to you, and then you should decide whether it is obvious or not. So again, I suppose I didn't say this. I suppose that U is also, actually it is very easy to generalize it to arbitrary covering hues, but I don't need it, and I prefer to prove what I need. So U is also a countable covering. So U, I say U alpha, actually it is U is U1, U2, and so on. Now I want to make a new covering. Again, locally finite and compact and countable and everything. V. So I want to arrange AV, and I do it by induction. Namely, I suppose that for some n, I already have this sets so that the Vi is in Ui, and I take the rest of them. This is V, this is U. And I assume that this is a covering. So my goal is to replace every U by a V. And the induction step is that I replace only some of them. Only the first n minus 1. My assumption is that the closures of VIs are contained in the UI, and also, this is still a covering. It is especially easy to do if n is 1, because in this case I don't need to do anything. If n is 1, then with the kind permission n minus 1 is 0. So for n equal to 1, we just do nothing and we are happy. Suppose that we already have this for some n, some positive n. Now I want to find Vn. First, let me take this covering and just forget Un. It is not a covering because one set is missing. Still, the union is something which is contained in x minus Un. You see, every point of x belongs to one of the sets there. So either it belongs to one of these sets or it belongs to n, no other choices. So the union is here. This set with your current permission again is closed. And now we consider the following. The union should be somehow, I want to denote this union by SW. So W is closed set. And what? It is so if this is UN, then this is the complement. W is not closed. W is certainly open. So, and this is X minus W. So points which are not in these sets. You understand? What can be said about this pair? UN is very much open, and this closure is compact. This is equally much. UN is open. This is very much closed, and is contained in a compact. Is contained in a compact set. Right? Well, now Vn is before your eyes. Just take any closed set, and we have a construction which gives this. Take a closed set, an open set, say that Vn contains X minus W, and Vn bar is contained in Un. For this we have a construction since since UN bar is closed, is compact. This is also compact. A closed subset of compact set. So this is we have this Vn. Now this Vn is contained this, so this is a cover. What next? So we can apply this induction now. And we get the full set of sets Vi. Right? Vn, Vn plus 1, V1, V2, V3, V5, V15, V so on. What remains? Yes, probably I erase this. So we have this set, sequence of sets, infinite sequence of sets, open sets. But still there one thing remains. Namely, I want to say that it is a cover. You see, on every finite step, it is a cover by our construction. But when we go to infinity, it becomes less obvious. More or less, actually, this may be even wrong. If we don't, for this construction, if we do not assume that the initial cover, if we do not assume that the initial cover was locally finite. Do you understand what I say? So the initial cover, why is this a cover? This is a cover by our construction for every n. But if we take a point P in X, it is covered only by finitely many U's. So P, and the neighborhood of P, is disjoint with um if m is bigger than some number. And this actually settles everything. Because if this point P is disjoint from um, then it should be contained in Vm. Look. Vn, let me say Vn. Say in the union of V's up to Vn. Vi is Ui, contains Ui minus what? Minus this and minus this. Now, if P belongs if P does not belong to this, then it means that P belongs either to Vi, if P is in Ui, belongs either to Vi or to this union, because Vi is a difference. If it belongs to Vi, that's okay. If it belongs to this union, it's also okay. So this is done. My friends, my time is almost over. I need to say one more thing, and I will say that basically next time. But still, have you ever heard such expression, partition of unity? You heard it, some of you. Do you know that it is actually very important? Not so important, so how to say, popular. We always used in constructions related to analysis, to differential topology, but actually to analysis which is soft enough. Let's say C-infinity analysis, not analytic. So what is partition of unity? Partition of unity is partition of unity, first of all. That is, it is a sequence of functions. And if you take the sum of all of them, it should exist and should be equal to 1. This is by itself not very interesting. We have some cover, some open cover, UI. Let it be. Actually, it may be not necessarily countable, but just easy to say. So the cover UI. Function fi is a positive real function, which smooth, takes value between 0 and 1. And its support, so this is 0 in the complement to some closed set which lies in UI. So in UI it may be not 0 on something, but in the complement to UI and actually to in the closure of this complement, it is 0 absolutely. If this UI is a locally finite covering, then at least no problems arises regarding the sum. Because if a family of series, F1, F2, F3, the supports form a locally finite family. That is, for every point there is a neighborhood which can touch only finitely many of these supports. Then certainly for every point, not speaking of neighborhoods, for every point these functions f1, f2 have only finitely many non-zero values. Why I insist so much on neighborhoods? Because to take just the sum, converging sum, it's all okay. It will be, you can do it. But if you want to check that it is well continuous, smooth, or something, you need some property similar to uniform convergence in analysis. And by this reason, I say that actually every point has a neighborhood where the sum is finite. Finite sums, you know, of smooth functions are smooth. So this is the result which I'm going to discuss next time. There are, for every, absolutely every, without any exceptions, open cover of a manifold, there exists a partition of unity inscribed in it, subordinated to it, in the sense that for every function, its support is contained in some of the elements of this covering. Unfortunately, next time I hope to do it today, but the time is over. Thank you.